In 5.3, we're going over logarithmic functions and graphs. But first I want to look at properties of exponents, and basically we're going to be using this chart of properties in front of us to simplify some exponential expressions. Right here on our first part, part A, we have a to the power of m times a to the power of n. And when we have something like this, we keep our base and we add our exponents. This is, let me give you an example of this. This is like having an x cubed times x to the fifth. Well, our base is x, you keep the base and add the exponents. Okay, so let's move on to the next one, b. In a to the m divided by a to the n, you keep the base and subtract your exponents as long as a does not equal 0, because that denominator cannot be 0. So let's just keep on with x cubed and x to the fifth. So if I had x cubed divided by x to the fifth, that would be x to the power of 3 minus 5, which is x to the negative 2. Okay, now this is a little bit different. A to the power of m, and you're raising the whole thing to the nth power. And when you do that, you keep the base and multiply your exponents. So let's keep with our theme. X cubed, and we're raising the whole thing to the fifth power. So this is an x to the eighth. See, when we had x to the eighth, we had the same base. We had a base and an exponent multiplied by another base, by the same base and an exponent. But here we just have x cubed, and we're raising the whole thing to the fifth power. So that would be x to the 3 times 5 power, which is x to the 15th power. Now, when you have an a to the m power and a different base, maybe a base of b, to that same power of m, you can say that that is ab to the m power of m. So that'd be like having x to the fifth times y to the fifth, and saying that that is x, y to the fifth. And the same thing with our division here. If you have a base to a power and a different base to that same power, just like x to the fifth, y to the fifth, different bases, but write them down and just raise that whole thing to the fifth power. Now, if you have a base to the power of a fraction, you can say that that is just like saying a is to the power of m over n. You can say that that is really a to the power of 1 over n, and the whole thing raised to the power of m. And what we mean by this, like what if we had x to the power of 3 over 5? It would look like x to the power of 1 over 5 cubed. Anything to the 0 power is 0, any base. And then right here at h, we can say that if you have an a to the m minus n power, you can say that that's equal to a 1 over a, and sort of flip your numbers there, n minus n power. Just like a to the 3 minus 5, we said up here that it was equal to negative 2, but it's also equal to 1 over a to the 5 minus 3 power, which is, and I just realized I used an a there and I used an x up top. I wanted to compare them. It's also equal to 1 over x squared. So because of that, whenever we have a negative exponent, we can move it to the denominator. And then right here at I, I'm sort of running out of room. But when we have an a to the power of m over n, I call these PR problems, public relation problems, because um, you have a power over your root. Okay, this is the um, nth root of a to the m power. So if I had x to the, let me come down here and write x to the 2/3 power, it would be the third root of x squared. I could also write it as the third root of x and square the whole thing. It will give you the same thing. So let's use that chart to work these first examples. In example 1, we have a base raised to a power multiplied by that same base raised to a different power. So what I can do is keep my base and then my exponents. So this would be 2 to the power of x plus 5. And right here on example 2, I have 2 to a power divided by that same base of 2 to a different power. So I keep the base and subtract the exponents. Now when you have a base raised to a power like 2 to the 4th, and then the whole entire thing is raised to a power, you keep the base and multiply the exponents. Now in this one, 1 over 3 to the negative 2, because that power is negative, just like if you look on if you look at H and how I said earlier, how I said you could write, if you compare part B up here to H, where I'm essentially working the same problem, you can see that when, like right here where x was the power of negative 2, I moved that base with the negative power to the denominator and it became positive. So right here on problem number 4, because I have a base to the power of a negative number, I can move it, if it's in the denominator, move it to the numerator. If it's in the numerator, move it to the denominator. So I'm going to move it to the numerator. I don't really need that 1, I'm just showing it for emphasis. So this is really 3 squared, which is 9. Anything to the 0 power is 1. A to the 1/2 power. This is what I call a PR problem. When I have a base that is raised to a power, looks much different than what we see in number 2 up here. That's a base to a power divided by a base to a power. Some people get those confused, but whenever we have a base raised to the power of a fraction, these are PR problems because I call them power over root, where the 2 is my root and the 1 is my power. So essentially this is just the square root of a. This is another PR problem. Write PR beside it if you need to. And this is the 5th root of a squared. And the square root of x just wants us to transform it. It's really simplified just like that, but we could sort of reverse that power, that PR rule that I showed you in example number 6 and 7. Remember 5 was the root and 2 was the power. Well, this has a power of 1 and a root of 2, so I could write it as x to the 1/2 power if I needed to. We just looked at properties of exponentials, and so now we're going to look at properties of logarithms. And you can see in the box up top that I have the properties of logarithms. This looks the same as the box on your paper. Now, as I read these statements about the logarithms, will you please listen to me and follow along and try to say them in your head? A lot of people mess up when they read logarithms, and it really can be very confusing if you get that mixed up. This is the logarithm of 1 base b, and it's equal to 0. So anytime there's a logarithm of 1, no matter what the base is, it will equal 0. This is the logarithm of b base b, and it equals 1. So when the logarithm is the same as your base, it will equal 1. Now, here the logarithm is the same as the base. It's the logarithm of b to the power of x base b. But because there was this power right here, it's just going to be x, because it's like saying, well, let me show you. The logarithm of b base b was 1, so that's like saying 1 times x, which is just x. Okay, and then when we have b raised to the power of the log of x base b, it will be x. And so that's easy to remember, because when you have a base and it's the base of an exponential and it's raised to the power of a logarithm that has the same base, it sort of all just goes away and you're left with x. So let's look at these examples. In example 1, you have a log of 1 base 50, and I told you when we have a logarithm of 1, it's equal to 0. Same thing in example number 2, the logarithm of 1 base 10. And then in example number 3, we have the logarithm of 5 base 5, and those just sort of go away and give us 1. Now in example number 4, ironically, it looks just like your property, and in your property that we have up there at 3, and it's the log of b base b, and that b was to the power of x, so it's like 1 times x, which just equals x. Now in number 5, we have the logarithm of 4 to the power of 25 base 4, and because the logarithm of 4 has the same base, it's 4, we're just left with the 25, much like we were just left with the x up here. Same thing in number 6. Log of 94 base 94 is 63, because that's all that's left. And I said that wrong. Log of 94 to the power of 63 base 94. Now we have b raised to the power of log of x base b. And when you have an exponential and its base is the same as the base of the log that it is raised to, it cancels and you're just left with x. And same thing here, you have a exponential of 2 raised to the power of logarithm 25 base 2, and the 2 in the base of the exponential and the 2 in the logarithm cancel to just give you 25. In number 9, sort of the same thing, we have that base of 3 raised to the power of a logarithm of x to the 5th base 3. Those bases are the same, they go away, you're left with x to the 5th. In number 10, I want to give you some background information. Just like if I have the log of x, that's equal to the log of x base 10. Whenever you see a logarithm and you don't see the base, you assume that it's 10. Well, we know that the natural log of x is equal to the log of x base e. A natural log is just a logarithm that has a base e, so they don't even write it there. And because the base is e of that natural log, the natural log and the e cancel out, and we're just left with x squared. So just remember that. Natural log and e undo each other. So we have some more examples to look at. We have the log of 10 to the power of negative 5 base 10, and that means that when we have the logarithm of 10 and it has the same base, the logarithm and its base are the same, you're just left with that power, and same thing right here, we're left with 2. Anytime you have the logarithm of 1, you get 0. And here we have the logarithm of 5 to the power of m plus n base 5. That logarithm of 5 and its base of 5 cancel, and you're just left with m plus n. Now here we have a base of 10 raised to the power of a logarithm of 4 base 10, and that exponential and the logarithm and its power have the same base, and you're just left with 4. And the same thing right here. The exponential and the logarithm and its power have the same base, so you're left with x plus 4. Excuse me, x to the 4th plus 1. These next examples are pretty fun because we're going to have to manipulate a couple of them a little bit in order to get the answer, because we're going to do it without using a calculator. The log of 9 base 3, I don't really have a rule for that, but I can change that 9 to 3 squared and still keep my log of base 3. And now my 3 squared, well, my 3 and the base of 3 cancel and just leave me with 2. The same thing right here, 64 is 8 squared. Okay, and I have a base of 2. But now look, my 8 and my 2 don't cancel, so I may have to rethink that. Instead of a base of 8, maybe try a base of 2. So let's see, 2 squared is 4, and 2 cubed is 8, and 2 to the power of 4 is 16, to the power of 5 is 32, to the power of 6 is 64. So instead of saying 8 squared, I'm going to say that 64 is 2 to the power of 6, and I keep my base of 2. Therefore, my logarithm of 2 and its base cancel, and I'm just left with 6. Now 100 is 10 squared, and remember that we have a base of 10 that we don't see, so it's just 2. I can rewrite this as 10 to the 1/2 power, and then you have that base of 10 that you don't see, and so we just have 1/2. Same thing right here. This is 10 to the 8/5 power. That base of 10 we don't see, and we're just left with 8/5. And this one's easy enough, just like that. That logarithm of 3 has the same base. Now, thankfully I learned those powers, those exponential properties earlier in this section, and so I can write the square root of 2 as 2 to the 1/2 power and keep my base of 2. Therefore my answer is just 1/2. Now a natural log has a base of e that we don't see, so the natural log of e cancels with its base of e, and we're just left with -5. That base of e right there, and we could say that was e to the first power, so we just have 1. Anytime you have the logarithm of 1, your answer will be 0. This one's a little bit confusing, and we're going to learn a change of base formula that would make this easier. But let's see, the logarithm of 2 base 8. I need that 2 to have a base of 8. And the only thing I can think of, I know that 2 cubed is 8, which means that the cubed root of 8 is 2, and I can rewrite the cubed root as the 1/3 power, and I can say that this is 8 to the 1/3 power, which is the same thing as 2, and I can write my base of 8, and therefore I just get 1/3. Anything to the any logarithm of 1 is equal to 0. So the definition of a logarithmic function, if b is greater than 0 and b is not equal to 1, so that is your base, okay? The logarithmic function with base b is defined by y equals the logarithm of x base b if and only if b to the power of y equals x. A logarithm is an exponent. We can switch them back and forth. So basically the thing to remember here is that the base of your logarithm will be the base of your exponent. We have these forms right here, exponential form and logarithmic form, and I think it's just as easy to just start diving in to some examples. So I told you the base of my logarithm will be the base of the exponent. So the base of the logarithm is 7, and you raise it to the power of what the logarithm equals. So it's to the power of 2, and it will equal the inside of the logarithm. So again, the base of the logarithm is the base of the exponential. You raise it to the power of what the logarithm equals, and then you set your exponential equal to the inside of the logarithm. The base of the logarithm is the base of the exponential. You raise it to the power of what the logarithm equals, and set your exponential equal to the inside of the logarithm. So our base this time is 1/5. We raise it to the power of 0 because that's what the logarithm equals. And it equals the inside of the logarithm. And that's interesting because 1/5 to the 0 power, anything to the 0 power is 1. And look, these follow our rules, but I can also set it up as the base of the logarithm is 7 equals the first power. 7 to the first power equals 7. And so we get a true statement there. So for this next part, I have to sort of switch gears in my brain for a little bit. And we just worked problems where we were changing logarithms to exponentials, but now we're changing exponentials to logarithms, and the same holds true. The base of the logarithm will be the base of the exponential, and the base of the exponential will be the base of the logarithm. What I like to do with these, I like to go ahead and write down log on everything. Look, that's half the battle right there, knowing it's a logarithm. Okay, so the base of the logarithm will be the base of the exponential, and the opposite is true. The base of the exponential will be the base of the logarithm. So for number 6, I know that it has a base of 25, and the power of the exponential is what the logarithm will equal. And what the exponential was equal to will be the inside of the logarithm. So right here, we have, see, the exponential is x to the negative 1/4. So the base of the exponential is x. That will be our base of the logarithm. And what the exponential, the exponent itself will be what the logarithm equals. And what the exponential equals will be the inside of the logarithm. We have a base of 27, and outside of x, and the inside is 3. Okay, here our base is 1/3. Remember that your logarithm will equal the power of your exponential, and the inside is what your exponential equals. So our base is 3. And our power for the exponential was -4. So that's what the logarithm equals, and what the exponential equals is the inside of the logarithm. So we're graphing logarithms, and it's refreshing because we've had a lot of examples of converting back and forth. But something also neat about it is that it's very similar to what we were doing with graphing exponentials. In fact, we approach it the same way with an XY chart. And in fact, before I graph the logarithm, I convert it to an exponential. That base of the logarithm raised to the power of what the logarithm equals will equal the inside of the logarithm. And so I can draw that XY chart, but watch here. If I choose -1, 0, and 1 for x, let's just say that x was -1, okay? Then I would have to say 2 to what power is -1? And I just don't want to do that. It'd be much easier to say -1, 0, and +1 for y, and plug the power in. So if I say 2 to the -1 power, that's a half. If I say 2 to the 0 power, that's 1. If I say 2 to the first power, that's 2. Okay, let me get a couple more so that we get a clearer picture. Let's say 2 and 3. If I say 2 squared, that's 4. And if I say 2 cubed, that's 8. That should give us plenty of points. So we're here at 1/2, and we have a y value of -1. Oops, I'm graphing it backwards. 1/2, -1 right there. -1/2. Okay, we got 4, 2, and 8, +3. And that gives us a nice picture of that logarithmic function. And now for a little bit more calculator work. It says to find the value of each logarithm using a calculator and round to 4 decimal places. So thankfully I have a logarithm key right here under the second option, and I'm just going to type in 8520. So 3.9304. Okay, and the log of 8.59, 0.9339. I'm going to round that to 0.9340. And then we have the logarithm of -3, but we can't take the logarithm of a negative. It's undefined, and our calculator actually tells us that. It says domain error, so that means that we can't do it. So I'm going to write undefined. Okay. So now for our next part, find the value of the natural logs and round to 4 decimal places. So the natural log of 9, so second Oops, we don't need to press second. There's an ln key. So natural log, that ln key is right underneath the log key, the natural log of 9. 2.1972. The natural log of 3, I'm just going to use that up arrow and change that 9 to a 3. And I get 1.0986. And then I do the natural log of 1 point, not 1 point, 0.000103. I get negative 9.1807. I'm going to put that as 1808. Negative 9.1808. And then we can't take the natural log of a negative either. I just want to show you that it says undefined, and that's our clue. Domain error. So I'm just going to write undefined. So for our last example, we're going to learn how to change a base theorem, and we're going to get to use some of those things that we learned how to type in the calculator. That really we get to use everything we've learned in this section. Because, see, I could say, well, what does this logarithm equal? Because I know that you could change it to an exponential and say 3 to what power equals 75, but I have no idea. I don't know that. So I need to rethink it. Since I can't think of that off the top of my head and it's going to be a decimal, I can use the change of base theorem for that. So if you have a log of n and a base of b, you take that logarithm of n and you divide it by the logarithm of your base. Okay, so all I have to do to find out what x equals, x will equal the log of 75 divided by the log of 3. And I'm going to round that to 4 decimal places and let you see what we get. Watch me type in this calculator really quickly. I'm going to say the log of 75. I then press equals to get that decimal. I don't want to have to write that decimal down and then divide it by the log of 3. I'm going to leave it there and press divide, and therefore it has ANS, so it has the answer that I just got divided by the log of 3. And so 3.929, it says round 4 decimal places, so 3.9299. 3.9299. And what's interesting is that we said that if you change that logarithm into an exponential, it would have been 3 to the power of x equals 75. Well, we just said that x was 3.9299, so 3 to the power of 3.9299 equals, that's right about 75. So let's use the change of base theorem on our last problem. We're going to say the logarithm divided by the log of the base, which is 5. And I'm just going to show you that one more time in our calculator. There we go. Log of 75, log of 130 divided by the log of 5, 3.024. So how are we going to round that? 3.0244 is what I'm going to say.